think that today we're going to talk about probability. And I think that probability is actually a pretty interesting thing to do. We've been talking about central limits, and we've been talking about, central limits, I'm way ahead of myself. We've been talking about central tendency, and we've been talking about frequency distributions, and those do have limits in them. But today we're going to sort of take a step to the side, think about something else, and then come back to statistics. Probability is a big part of statistics, and it's important that we're able to sort of work our way through what's happening. And as is usual, anytime we break into a new section, a totally different section, it's time for us to introduce some new words. So let's talk about chance and probability. First of all, what is probability? Probability is a number. It's a number that lives in between 0 and 1 on the number line. And so we normally write it out as a decimal. If I score 1, I'd say that I have a 100% chance of something happening. If I have a 0 as my probability, I say that's something that doesn't happen. So we have this idea that all things live in this range, this continuum between 0 and 1, and if they're more likely to happen, they'll be closer to the 1 side, and if they're less likely to happen, we expect them to be closer to the 0 side. Now you should be aware that some recent advances in quantum whatsits are indicating that possibly probability doesn't have to actually add up to 1. But that's okay. We're in the business of modeling things. We're not in the business of making a perfect replica. If we were, we'd have to always recreate our problem in perfect detail, and the only way to do that is to recreate the actual problem, and then we haven't gained anything. So, I don't know, maybe sometimes people are like, oh no, something's wrong now. No, this is a model, and our model continues to be pretty useful in a lot of scenarios. Should we incorporate new data into our model? Absolutely. But we don't need to worry too much about the fact that maybe, just maybe, our model isn't as incorporating all the latest and greatest developments as it's got. It's still pretty good. Plus, this is intro stats. We're safe. So this is probability. We generally, in probability, talk about events. And these events are going to be chances of things that happen, and we want to talk about how likely those events are to occur. So let's call one of our events A. A is an event. It might be the chance that I decide to start dancing a jig in the next 2 seconds. It might be the chance of getting heads or tails as I flip a coin. Who knows? But this is my event. And using function notation, I write P of A. P paren A close parens. And this is the probability of A. The chance that A will occur. Think of this as a machine. And this is a capital P, not a lowercase p. We'll use lowercase p for something else. Think of this as a machine that takes inputs, and I can feed different events into it. And if I decide to pop in the event A, it says, okay, I can tell you the chance of that happening. Maybe that's 0.48. Who knows what A is? But again, think of this as some p function, and it can take an input. In this case, we pop in A, and that tells me my probability of A occurring. Once we've got this idea that this is how probability works, then we know that this p function, p of A, is going to live somewhere on this scale between 0 and 1. 0 if it doesn't exist at all, 1 if it's going to be totally existing there. So, let's take a look at the different types of probabilities we can have. How we might calculate those chances, I mean. We could use intuition. I could look at something and say, you know what, it's about this much. How would that work? Well, even before I ever really started studying classes, I remember the first time I sat down in one of my classes, and my professor told me, look left, look right, at least one of those 3 people, including yourself, is not going to be here by the time we're, 3 weeks from the final, something like that. It was very scary. That wasn't absolute truth that 33.333% of the class was going to drop. It was just conventional wisdom. It was intuition. It seems to work this way. If I see that the weather is labeled as a 60% chance of rain by the weatherman, maybe I don't always trust the weather person, so I think to myself, it could rain, it might not rain. 50-50. Another way to do this is called relative frequency, and we already met relative frequency back when we first did histograms. Frequency over little n. Number of times something occurs divided by the total number of trials we ran. So with this type of probability, it's maybe a little bit more accurate, provided you've already seen all the things that can happen. For example, let's talk about weather phenomena. Possibly, if I looked at all the weather phenomena that occurred in Texas in the last 50 years, I would see a couple earthquakes in some places, but not a lot, just a couple. Unlike maybe California, where I'm from, where we would have lots of earthquakes. But mostly hurricanes is what happens in Texas. So if I was trying to figure out the relative frequency of earthquake, I would have about 2 or 3 up here on the top, divided by, let's say, hundreds of hurricane-type events, plus those couple of earthquakes. And so I would say there's a very small probability of earthquake in Texas. Lastly, you could assume that all the events are equally likely to occur, and this is called equal probable outcomes probability. The problem with this one is that, you know what hasn't happened in Texas in the last 50 years? Volcano, to my knowledge. I don't believe there's been a volcano in Texas in the last 50 years. And that's nice. There probably won't be one in the next 50 years either. We don't tend to think of that as being a real risk here, but it could. We could have drastic global upheaval. A ginormous meteor could come and hit the other side of the Earth and cause some real big problems in terms of volcanoes in Texas. So if you're talking about equally likely outcomes, then you might say, well, what's the chance of an earthquake? Well, we're talking about earthquake, and then I could start listing in my head natural disasters like volcano, hurricane, tornado, earthquake, and, I don't know, drastic fire or something like that. And I could put the desired outcomes over the total possible. In general, something between these two tends to be most reasonable. What's the flaw with the relative frequency business? Well, it comes down to that sampling frame error we talked about before, where maybe we have the sense that just because I've measured my natural disasters in this time frame doesn't mean that something different happens over the long term. I think of my friends who own a house that's on what they call a 50-year floodplain. And if you measure the relative frequency of flooding in the last 20 years, their house would have been perfectly fine and dry, most importantly. But if you measure it over all likely outcomes, maybe the chance of flooding is a little higher for them under this scenario than it is under relative frequency, because flooding in that place happens every 50 years, more or less. So, we have this idea of events that occur. We have this idea that P of A tells me the probability of that. And we have this further idea that number of desired outcomes divided by number of total possible is an interesting thing to do for probability. So where does that leave us? Well, it leaves us with some more words to talk about. The first of those is an interesting law that we have. It's called the law of large numbers. And as I mentioned, my friends on the floodplain might not do well if they only took the last 20 years of data, because they might think, this house is safe. Nothing bad will ever happen. The law of large numbers says that as we do more and more and more of this probability business, as we look at more and more and more n, as n increases to be very large, then the frequencies that we expect in our calculations should more closely match what we would think actually will happen in terms of all of life. In particular, it says, as n increases, f over n approaches the actual. And I'll put actual in quotes, the actual P of A. Because of course, all we can ever do is model. And so we think, well, it's highly likely that this will happen, but as you do more and more and more, you get the actual legitimate number. From there, we can start to calculate a couple things, and so we have a couple more words that we tend to talk about. So an event, like A, is the collection of our desired outcomes divided by our total possible, and an event lets us figure out what's going to actually occur. So events have some outcomes. And once we have our event, then we talk about different types of events. And that's mostly what we're going to discuss in this section, this next set of sections, this chapter. We can have simple events with just a single outcome. We can have more complex events, where things chain on themselves just a little bit more. Before I talk about some differences between simple events and complex events, let's get some words and some ideas chained up together. The total probability should always sum to 1. That's going to be one assumption we make, and it is an assumption, I admit. And also, we're going to suppose that as we chain our events together, you might have a couple different groupings of them. So there's the probability of A occurring, and there's the probability of A not occurring. Not A is written as A with a little c in the subscript, superscript there. Think of almost like an exponent, A squared, but it's AC. And this is what we call the complement of A. And complement is the chance of A not happening. So let's say this. I could either get coffee in the morning, or I could not get coffee in the morning. The probability of coffee for me is quite high, but the probability of not coffee does exist. Together, those add up to be everything that I might do for my morning drink or the lack thereof, and that should add up to 1. But just because I choose not coffee doesn't mean that I'm going to drink tea. I might choose to drink soda, or I might choose to drink water, or I could choose to drink nothing. So this idea of not A, this complement business, is rather interesting. And since they should add up to 1, we have a formula. The probability of A plus the probability of A complement equals 1. Now, I might decide to separate A complement up into other things like coffee and, well, that's A already, but I might have tea, or I might have an energy drink, or I might have soda, or I might have water or juice. So we could separate A complement maybe into other things later, but we can also subtract the probability of A off both sides. And we can know that the probability of A complement is equal to 1 minus P of A as well. So we can do some calculations and work back and forth between a couple different pieces of things. All right, so let's talk about some not so simple events. Let's talk about a couple things that happen maybe if we chain things together. I think this video probably can encompass several aspects of the chapter on probability, and we don't have to separate those out into any particular thing. I think this chapter is pretty straightforward. It's not too scary, particularly if you look at the examples of the text. Just work through the examples and life becomes pretty good. So let's take a look at some probability things that I might discuss. I don't think that's going to be safe. Simple events might be things that involve a very, very straightforward action. So let's talk about flipping a coin. If I stand here and hold out a little coin in my hand and flip it, it could either go to heads or it could go to tails. This incidentally is called a tree. I've drawn this little arrow here and it shows you the different places I might go, heads or tails. If it's a fair coin, we would imagine each of these to be 50-50 chance, right? So I'd have 0.5 and 0.5. I would write the probability of flipping my coin and getting heads. So coin heads there is going to be 0.5. And the probability of event flipping my coin and getting tails is going to be also 0.5. We have this idea here. That's a simple event. What if I flip my coin again? Flip it twice. Well, then more things might happen. If I flipped it heads the first time, that doesn't mean I can't get tails the second time. So if I continue on with my tree, notice my tree starts to get just a little bit bigger as I flip it a second time. Again, still, it's a 5% chance in each spot because the coin has no memory of what's happened before. But something happens. I say the coin has no memory. What do I really mean by that? I mean that this is an independent event. The coin doesn't care what happened before when you flip it a second time. It just continues on. So there's no real worry and there's no real fear about anything happening first or second. It makes a difference when we look at the big picture, but from the coin's point of view, it's just getting flipped. It doesn't know any better. And when you've got this process of multiple flips for independent events, we use what's called the multiplication principle. If I want to figure out the chance of flipping heads twice in a row, I would take 0.5 and multiply 0.5. And 5 times 5 is 25, but 2 decimal points there would give me 0.25. And that would be my chance of getting heads twice. 5 times 5, again, 0.25. All of these are going to be the same. So I can multiply down the branches of my tree and get this probability. Notice if I talked about relative frequency, I could do the same thing, because as I stand over here at the far edge after I flip my coin, I could either have double head, head tail, tail head, or tail tail. There's 4 different ways this could happen. There's 4 different total possible outcomes, and if I want double head, there's only one way that that could have occurred. So number of desired outcomes divided by number of total possible gives me that 1/4, which of course equals 0.25. So we have this idea that we can multiply ourselves through independent events. So let's take a look at some other things. If my events are what we call mutually exclusive, we tend to not multiply them. Instead, we add them. So we've got independent events, and we have mutually exclusive. And we talk about probability of A or B equaling P of A plus P of B. What are mutually exclusive events? They're things that are completely and utterly separate. Think A and A complement, for example. I can't both have coffee as my morning drink and not have coffee as my morning drink. That would be mutually exclusive. My favorite example is being able to vote Democrat and Republican. You cannot elect a Democrat and a Republican as president unless you're doing voter fraud, personally. Still, the chance of a Democrat or a Republican being elected into U.S. politics is actually probably rather high because, let's face it, if you go to third party, you're throwing your vote away. Do not come murder me. I'm being apolitical here, but still, you're throwing your vote away. You know, it's a two-party system. That's how this country works. Democrat or Republican. These are mutually exclusive events, and so we don't multiply them together I don't know, maybe there's a 45% chance that you'll vote Republican, a 45% chance that you vote Democrat, and there's just a 10% chance that you'll do Green Party or, I don't know, Libertarian or something like that, and there's thousands of others. I guess we even have a Communist Party. If you ever look at the ballots, you'll find like 59 different little parties that come out of the woodwork. But the point is, you add these together and you say, well, look at that. There's a 90% chance that we're going to elect ourselves a Democrat or a Republican, and that makes sense. So we've got mutually exclusive events. What if you don't have mutually exclusive events? What if you've got events with a little bit of overlap? What if I have a, let's see, something that's not mutually exclusive. I guess normally they draw out a picture like this. You've got event A and you've got event B. And if they're mutually exclusive, like Republicans and Democrats, then we tend to draw them like this, and there's no overlap there in the middle. But sometimes you might have some probability of things that do have overlap. So let's say that A is the chance that I drink coffee. B is the chance that I drink some liquid. Liquid of any sort. And out here in no man's land is the chance that I just choose not to drink anything in the morning. And maybe the chance overall that I drink coffee, we're expecting P of A for me to be somewhere close to 0.8. The chance that I drink some liquid is maybe, I don't know, 0.1 because I choose to have orange juice. But B, remember, is any liquid, so there's that 80% overlap with coffee plus the 10% of drinking some OJ. So the probability of B is something like 0.9. There's that massive overlap here. If I want to find the probability of liquid in general, first of all, I've got to draw myself a slightly better picture, right? Because the way I've chosen this, here's liquids, here's coffee. Coffee's totally inside here. This is the OJ area. You get the idea. This liquid in general should be the probability of A plus the probability of B minus the fact that I'm getting ready to double count that whole coffee area. Got that overlap region. All right. I think that is Formula 8, and we've got this calculation, and we want to cut off the double overlap. It would be silly. Maybe I can shade these areas in. So try not to spill my coffee. You want to subtract the overlap because notice that I double shaded this area. I'm double counting him. Now that wouldn't be entirely fair to count that for probability terms.